Hello everybody, my name is Tristan Hagerman and I will be doing the recap from November 20th, 2018. In this lecture we introduced the concept of a common filter. So, a couple of methods that we learned so far in class is the initial orbit determination, which requires 3 observations. And then we've also learned LUMV, which is a least squares method for orbit improvement, which uses a large batch of observations. Now, how can we continuously improve our orbit without continuously increasing the size of this batch of observations? One option is for us to maintain the current batch size by continuously deleting the old observations to maintain the size of our observation pool, in which case we can continue to use our standard LUMV, but we lose our old observations in the process. A second technique to this would be to use a sequential process, such as a sequential LUMV, which is not addressed in this class, or an extended Kalman filter for a minimum mean square or MMS error. So, in general, this process will go in this order. We'll do an IOD with our first 3 observations to get an initial guess for our position and velocity. Then we will use a batch method for the next set of observations that we do to improve our estimate and to get a covariance. And then using this, we can use a sequential method to continuously improve our orbit using an iterative process. So in this process, we're going to propagate from our previous measurement until the time of a measurement, in which case we will update our information and then use that information to propagate and continue cycling back and forth iteratively. So first we're going to need to propagate our mean. So let's establish our system dynamics. Our x dot state dynamics is equal to the state dynamics matrix F times the state plus M, which is simply a shape matrix to map our W, our white noise process, into this. From our white noise process, we can get a QS, which is a power spectral density matrix. Then the mean is given by the expectation of the state at a time t, and thus m dot is equal to the expectation of x dot. By applying the system dynamics to the state x dot, we get that m dot is equal to simply the dynamics of the system times the mean. Now, the state estimation error covariance, P, that we're going to be propagating is equal to the expectation of the error times an error transpose. We're going to define this error as the state minus m, the mean, which is simply the expectation of the state at that time. So the error dynamics, E dot, are equal to x dot minus m dot. And then we continued on with a fairly lengthy derivation to arrive at the covariance matrix is equal to the state transition phi times p times phi transposed times the integral from rk minus 1 time to the current time of the transition matrix times the mapping matrix times the QS power spectral density times the mapping transpose times the transition transposed. Now, if we simply define this integral term as QC, which is our process noise covariance, we can rewrite the covariance as simply P equals phi times phi transpose plus QC, and this is the covariance at the previous time step. So we can propagate this by one of 2 methods. Firstly, we can propagate the transition matrix by saying that phi dot is equal to F times phi. And then we can propagate the noise covariance QC matrix by saying QC dot is equal to FQC plus QC F transposed plus M QS M transposed. And then we can simply use these to find at our new time t the covariance matrix. Or we could simply find the covariance matrix directly by finding its dynamics with Fp plus Pf transpose plus MQM transpose. Both these methods depend on a mean and covariance from a previous update. So to do this update, we're going to say that our measurement z will take the form h times the state plus L times the measurement noise Vk, where the excitation of V times V transpose will give us this R, which is the noise covariance. Now if this measurement is linear, we can say that Zk hat is equal to the expectation of Z, which takes this form, which is simply H times the mean that we propagated to this time step before doing the update. So our updated mean after the update is equal to the mean before updating plus K times Z minus Z hat. Now this K is called the Kalman gain, and we're going to define it in the next slide. So the cross covariance CK is defined as the expectation of the state minus the mean before updating times Z minus Z hat of the measurement transposed. For a linear measurement, this simply becomes the covariance before updating times H transposed. The measurement covariance, WK, is the expectation of Z minus Z hat times itself transposed. For linear measurement, this simply becomes HP before updating H transposed plus LRL transposed. We can use these to calculate the Kalman gain from the previous slide. The KK is equal to the cross covariance times the inverse of the measurement covariance. And now we have everything we need to calculate our updated covariance matrix, which is simply the covariance from the previous step minus CK transposed minus KC transposed plus KWK transposed. And the final slide is simply the last page that we saw during the class, which gives the most important equations that are necessary for us to go through this iterative process. And that ends my lecture. Thank you.